Alright, so let's say for our next example, I'll start on a new page. I don't think this is going to finish up on this half a sheet. Oh, you want to still writing? Alright. Okay, so let's say for our next example, if we want to find the sum of 9 to the third power plus 10 to the third power plus 11 to the third power plus 12 to the third power all the way to 18 to the third power using summation, formulas, and properties. Okay. So for this one, 9 to the third plus 10 to the third plus 11 to the third, 12 to the third, all the way to 18 to the third power. That's just equal to the sum from I equals 9, because we started at 9, to 18 of some I to the third power. So all we did, if we plug in 9, we get 9 to the third, plug in 10, 10 to the third, 11, all the way up to 18, where we stopped. Okay. Now we have to actually find the sum. But it has to go from 1 in order for us to use our formulas. Can't use it if it starts at 9. Okay. Now the one thing we do know, that the sum from I equals 1 to 18 of I to the third, we can actually stop it at 9. Well, start at 9. So let's say we have the sum from I equals 1 to 8 of I to the third plus the sum from I equals 9 to 18 of I to the third. Okay, so all we did was go ahead and we broke it down a little bit. All right. Now, if you remember, put that in a little side note. The sum from I equals 1 to n of I to the third is equal to n squared times n plus 1 squared over 4. Okay. Now for this one, actually we have to isolate this by itself before we can use that. So we subtract the sum from I equals 1 to 8 of I to the third on both sides. Because remember, we're solving for that. So that means our summation, make sure I give that enough room, from I equals 9 to 18 of I to the third is going to equal from 1 to 18 minus from 1 to 8.
Maybe I missed that part. Why is it 8 and 18?
Oh, because we broke this summation down. We went from 1 to 8, and then we picked up on the next one. Then we went from 9 to 18. Okay, so that will be minus the sum from I equals 1 to 8 of I to the third. Okay, so now we can use this formula because we now have both of these with a lower bound of 1. But for this one here, our n is equal to 18. But for this one, our n is equal to 8. But they're both I to the third. So that means this is going to equal 18 squared times 18 plus 1 squared divided by 4 minus 8 squared times 8 plus 1 squared divided by 4. Okay. And this actually gives us 29,241 minus 1,296, which ends up being 27,945. All right. Yes.
So would you be able to still like do this if the i's were raised to a different power, like the exponents?
With them raised to a different power,
yeah, like
only
I
if
to the third, like
only if you could somehow,
you'd have to find something like common between them.
yeah, somehow find common between them. So if you had, let me see, I'm trying to think of one way that would work. Because normally they just stop at I to the third, because when you get to I to the fourth, fifth, sixth, the formulas are really long. So you shouldn't run across any higher than that.
Okay.
At least not here. Probably when you go into, I'm trying to think what class you would see it in, it gets a little more complicated. They usually stop at I to the third. All right. Okay. Oh, let's do. Okay. Okay, so we'll do one more example and then show you why we started with these in the first place. Let's say if you want to evaluate the sum from I equals 9 to 21 of I squared, using just the properties and formulas. All right, so with this one, you want to remember that the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 divided by 6. Okay. Now this one doesn't start at 1, so we have to kind of manipulate it a little bit. Okay, so we know that the sum from I equals 1 to 21 of I squared is actually equal to the sum from I equals 1, and since this is at 9, we'll stop this one at 8 of I squared plus the sum from I equals 9 to 21 of I squared. Okay, so you go from 1 to 8, then you go from 9 to 21. Okay. But since we're trying to solve from 9 to 21, we just subtract the 1 to 8 from both sides. Where these two disappear. That means we have the sum from I equals 9 to 21 of I squared is equal to the sum from 1 to 21 of I squared minus the sum from 1 to 8 of I squared. So they're both starting at 1, so that means we can use the formula. Where on this one, your n is equal to 21, and for this term, your n is equal to 8. Okay, so that makes sure you bring that up just enough. So that means this is going to be 21 times 21 plus 1 times 2 times 21 plus 1 divided by 6 minus, using the same formula but instead using 8 this time, 8 times 8 plus 1 times 2 times 8 plus 1 divided by 6. Okay, so this one ends up giving you 3,311. Oh, make that look more like an equal. Minus 204. Which would give you 3,107. All right, so any questions on that one? All right, so whenever they give you a problem like this and they're starting at something other than 1, all you have to do is just start at 1 and kind of break it apart into 2 separate summations. All right. Now the reason why we had to do all that is because now we're going to go into the area of a plane region. Okay. And a majority of this section, I would say almost 90% of this section, as far as like the proofs, will revolve around the area of a rectangle. Which is equal to length times width. Uh-oh. Okay. Now that's okay for a rectangle, but what if you have a function that's kind of oddly shaped? So let's say, what about the area of a function? Okay, so let's start here, where we'll get some function between a and b. So if we do that, make that a little bit longer. And let's say this is our a and this is our b. And what if we want to find the area underneath that whole oddly shaped function? Well, the only thing we know for a fact is that the area of a rectangle is length times width. So we can kind of get an approximation by putting a rectangle in there. And unfortunately, that leaves all of that unaccounted for. But it gives us somewhere to start. So this is just a rough approximation of the area of our function. So not great because it leaves a whole lot of open space, but like I said, it gives us some place to start. But instead of one rectangle, what if we tried 2 rectangles? Okay, so we have our x, we have our y, we get our function, and we go from here to here. And once again, we go from A to B. Okay. So if we do 2 rectangles this time, so we go from here to here, and from here to here. Okay, so this is our 1 rectangle on our 2nd rectangle, which still not great because you still have all that empty space you haven't accounted for. But it's less empty space than you had over here. Okay, so with 2 rectangles, you get a little bit better. So it's a little better approximation. Not great, but a little bit better. So what if we tried 5 rectangles? So if we drew this one more time, we have our graph. And once again, we're going from A to B. But this time, we're going to go with 5 rectangles. So first rectangle, second rectangle, third rectangle, fourth rectangle, and our 5th rectangle. Okay. Which isn't bad because we only have this little bit of space unaccounted for, which is a whole lot better than what we started with. So you can see as the number of rectangles increase, our approximation gets better and better and better. So you can imagine if you'd use 10 rectangles, 1,000, 1,000,000, a billion. It just keeps getting bigger. So the more rectangles you can put in there, the better your approximation will be. Would increase if you had, let's say, 25, 1,000, or 1,000,000 rectangles. Okay. Like I said, once you have like a whole bunch of rectangles in there, because here, in order to find this actual area, you would just have to add rectangle number 1 and rectangle number 2. For this one, you'd have to add rectangle 1, 2, 3, 4, and 5. Just to get your approximate area. Okay. Now, if you notice with these rectangles, each one of them they're underneath the graph. And by them being underneath the graph, their right corners are actually on the graph. Okay? So you can see when the slope is decreasing and your rectangle is underneath, the right endpoint is going to touch the graph. Okay? So rectangles under the function are called inscribed rectangles. Okay. Or known as your lower sum. Okay. So for your inscribed rectangles, so if we start off with the one we had there, and again going from A to B, move this up just a hair, we see that our function is decreasing. So our inscribed rectangles all have a right endpoint that touch the graph. So our right endpoint touches the graph or the function. Now, if we had that let's say instead of decreasing, you had a graph that was increasing. So some increasing graph. Okay. So if you wanted to keep all your rectangles underneath it, you'll notice that the left endpoint would have to touch the graph. Okay, so if it's increasing, the left endpoints touch the function. Okay, it's a really minor detail, but it actually has a very big role in what we're going to do a little later. All right, any questions on that so far? Okay. Okay, so what if the rectangles are over the function? Okay. So let's start with our same graph. So we have a graph here. It goes from A to B. Let's say this is our A, and this is our B. But this time, instead of going underneath it, our graph goes over it. No better yet, let's start right up at the top. Okay, so we have a rectangle. We go up there, and say we go down to here. Okay, which gives us a pretty decent approximation. The only problem is we have all that extra space, and we still didn't account for that. But just like before, it gave us some place to start. Okay, so this is just the approximate area. Of our function. Okay, so just like before, what if we have two functions? Okay, we get the very same graph from A to B. Okay, but this time we want two graphs that happen to go over the function. Okay, so if we get two graphs, once again we have our first rectangle and our second rectangle. Like I said, we cover more space under here, but we didn't get there, and we have kind of missing space up there that we have too much of. Okay. So it'll give us the area, but it'll give us a higher area because we have all that missing space. So it's a little bit better. Not much, but a little bit better. Oh, actually, this should stretch all the way to end, so these two should be the same length. So that end there shouldn't be there. Oh, and yeah, I'll just bring that down to there to make it. There we go. Yep, and this one actually shouldn't be here. So let's say if we make this a little bit longer. So it should actually go all the way to A and B. There we go. And clean that up. There. Good as new. Okay. So again, it's a little bit better. Not much, but a little bit. Okay. So what if we had 5?